So today we're going to be looking at a heat exchanger where we have some flow rate of a hot stream and some flow rate of a cold stream. And we're going to be deriving an expression for the heat transfer rate dq using the differential area and a heat transfer coefficient. So as you go through the pipe, obviously the warmer fluid is going to lose heat to the colder fluid, and the temperatures are shown in this graph. Forgot my x-axis, I guess. But so the initial difference in temperatures is going to be delta T1, the final difference in temperatures, delta T2, and at any point along the graph, the difference in the two temperatures is going to be delta T. So we can start off by coming up with an expression for this dq. dq is going to be equal to the mass flow rate, and this is for the hot. And this one will be for the cold. But dq will be equal to the mass flow rate times the heat capacity at a constant pressure for the hot fluid times dTh. And then same thing for the cold one. Sorry, the hot is losing heat energy, so we're going to make that negative, while the cold stream is gaining energy, so we're going to make it positive. And then the CH and the CC we have here, this C sub H and the C sub C, we can express this mass flow rate times the heat capacity as the heat capacity rate. So again, we're going to have hot dq is equal to CH dTh, and this cold is equal to CC dTc. So from here, we have dq is equal to some heat transfer coefficient times the difference in temperature between the two streams times the differential area that the heat is able to transfer over. And we have delta T is equal to just the difference in temperatures between the two streams. And if we take the derivative of this, we have d delta T is equal to dTh minus dTc. And if we go back up to our dq here, we also have TH is equal to dq divided by CH. And same thing with the cold stream, we have TC is equal to dq over CC. We can go ahead and plug these in to our equation we just came up with. And we have d delta T is equal to, now I'll go ahead and pull out the dq, we have dq, then 1 over CH minus 1 over CC. So now we have two expressions. We have this expression for dq, and we have this expression for d delta T. And this d delta T has dq within it. So we can go ahead and substitute. So we're going to have d delta T is equal to u delta T dA times 1 over CH. Let me rewrite this parenthesis. dA times 1 over CH. And I'll actually pull out the negative here. So we have 1 over CH plus 1 over CC. And we'll go ahead and divide across and then integrate. So we'll have d delta T over delta T is equal to negative u dA over, or times 1 over CH plus 1 over CC. And then we'll go ahead and integrate from position 1 to position 2 on each side. So we'll have the ln, the natural log of delta T2 over delta T1 is going to be equal to UA times 1 over CH plus C, or 1 over CC. from here, we want to get rid of this expression here. We want to get rid of the CCH and the CCC, or the CC. So we have DQ, or sorry, not DQ, the total heat exchange for the hot stream is going to be negative because it's losing heat. So we have negative CH times dTH, and dTH is just equal to the temperature at the inlet. And let me rewrite this so we know that it's the hot stream. Temperature at the inlet minus the temperature at the outlet. Sorry, that's a little cramped. Now we can do the same thing with the cold stream. We have Q is equal to CC times dTC. And we'll go ahead and substitute. We have Q is equal to negative CH times THI minus THO, and then it'll just be the same thing with the cold but without the negative. And then actually for the positive, we're going to distribute this negative through. So we're going to have Q is equal to CH times THO minus THI. Divide across to get 1 over CH. We'll have 1 over CH is equal to Q TH outlet minus TH inlet. And we'll go ahead and substitute that in. So we have ln of delta T2 over delta T1 is equal to negative U times U times A times this is over Q, not times Q. So we have THO minus THI over Q plus TCI minus TCO over Q. And then we'll just move the Q out. So we have ln delta T2. And again, the delta T2 and the delta T1 are just the difference in temperatures at the 2 points that we choose. So you have delta T2 over delta T1 is equal to negative U A over Q THO minus THI plus TCI minus TCO. And so from here, we'll continue. We have ln of delta T2 over ln of delta T2 over delta T1 is equal to negative UA over Q times THO minus THI plus TC minus TCO. Sorry, that's TCI there. And then we have, if we flip some terms around, we can get delta T1 and delta T2. So right now we're going to have ln of delta T2 over delta T1 is equal to negative UA over Q. So we need THI minus TCI for delta T1, and we need THO minus TCO for delta T2. So to get those forms of the equation, we have, let's see, right now we have THI plus TCI, so we need to flip that around. We can have THO minus TCO, which is delta T2, minus TCI, minus THI plus TCI, minus TCI, which is delta T1. So let's rewrite this again. We have ln delta T2 over delta T1 is equal to negative UA over Q times delta T2 minus delta T1. And then we're going to go ahead and solve for Q. So we'll have Q is equal to negative U times A times delta T2 minus delta T1 all over ln of delta T2 over delta T1. And we'll just distribute this negative through. So we have Q is equal to UA delta T2. Sorry, it's going to be delta T1 after we distribute the negative minus delta T2 all over ln of delta T2 over delta T1. And sorry, I had actually made a error in my sign back up here. So these two are actually flipped. We have delta T2 minus delta T1. Spoiler alert, I kind of made a countercurrent heat exchanger here. Almost, not quite. So this part here is the log mean difference of the two, or the log mean of the two delta T's. And we can use the identity A minus B over ln of A over B equals B minus A over ln of, oh, these are capital when they shouldn't be. There we go. Ln of B over A. And we can use that identity to say Q is equal to UA delta T1 minus delta T2 over ln of delta T1 over delta T2. And that identity allows us to show that the heat exchange between or the heat exchange in a countercurrent heat exchanger is the same as the heat exchange in a cocurrent heat exchanger.